Hello, everybody. This is going to be a longish demo where I try to explain our binary search tree studio from the view of a client. And in this case, I want you to imagine we're going to build a binary search tree that's going to be, house the student database at the university. And a student is just this record, which I have nowhere near the amount of information that the university tracks on you, but it's just first name, last name, WUSTL key, your Barabucks balance, and I have a list of courses that you might be in. I've just made that rather simply a string and an int, so you imagine CSE 425. You can imagine a lot more information on a lot of these things. Rather critically, this binary search tree is going to hold each value, each item at each node is going to be one of these students. But when I want to look up something, like if I want to find a student, it makes sense that I would not pass the entire record itself, because why would I need to find it if I already had the information? So it's nice to be able to pass some key. In this case, it makes sense, I think, to use the WUSTL key. It'll be unique. And it's just a nice, everyone has one. It's a nice way to look it up. So let's look at the signature for this binary search tree. It's already starting to see this sort of like when you make a tree, it's going to be this alpha kappa tree. The alpha type in this example is going to be student. That's the value that's going to be at each node. The kappa is going to be the key we look it up for, or the WUSTL key, right? And when I create an empty tree, I'm going to pass one of these compare functions and a toKey function, because when I'm running down the tree, I'm going to need to take, like when I insert it, I'm going to take the actual alpha and convert it to a key, and I'm going to be looking at the keys of all the values that I find. So the compare function will compare two keys. So this is going to take a kappa and turn it into an order. Order is just a standard thing in ML that's, less, equal, or greater, right? You're probably familiar with this with all compare functions. It's useful in sorting and searching and stuff like that. And the toKey function is going to take any item, as I was talking about before, which is going to be really handy, any item alpha, the value at the node, and turning it into what the key is. So I can use this compare function to find things and everything like that. So after we created a tree, I made this create simple tree for anybody. You can just have a tree of integers if you want, and look them up by the integer. And I just included that for you here. That has the you don't have to implement this function. I provided it. It implements this toKey function as the identity, because it just goes from the value to the value. But the three main functions on your thing are going to be to insert a new key. That will take a tree and some value to insert into it. That's going to return back the new tree, because it's going to be a mutable tree, an immutable tree, and also whether or not an optional value of whether or not it replaced anything. So if you're actually replacing some value, it'll return back the old value for you. And it's nice when utilities return the most useful information they can. Remove is going to pass in the tree that it wants to remove from and some key. So in this case, you would say sort of remove somebody's WUSTL key. It'll return you back the new tree and an option of whether or not it actually was there. It will return you the entire alpha value of what used to be there, if anything. Find just takes a tree and a kappa, and it returns you back that value for that key if it was there. So it's like, again, optional. We could build any number of higher order functions on this. We're just going to build fold. LNR does the left side, the node, and then the right, and RNL does right, node, left. This one is useful for consing, so that's what we're going to use today. ToString is just a function you can build that's helpful in debugging, and when exception fails, it's nice to have this filled in so that it'll work. So rather critically, let's come back to our example. As I said, the student has these, this is the type of the student, this is going to be alpha, and we're going to pass in a string that is the WUSTL key to look up, and that's going to be our kappa for this example. So to get going, let's get going. So binary search tree, we're going to create an empty tree, and that's going to take a compare function first. Nicely, because it's a string, it has a compare function. There's also an integer compare. You could write your own function that took two things and returned lesser, less, equal, or greater. We're just going to reuse this for now, which is fine. And then a function that turns a student into WSTL-key. And so let's just do that as an anonymous function. I'm going to define, let's just call students in this case, stu for short. And if we take a stu, I'm going to return back, and I'm loath to not do pattern matching. When it's a record that gets really long, is probably the only time I'll do this. It's going to cause a little bit of a problem, but if I take the WSTL-key of stu, right, and if I just run this, let me comment out the rest of this whole program just so we can see the little bit at a time. So if I run this client right now, you can see that we got this unresolved flex record. That's because it doesn't know if this is a student or it could be just something with this, just anything with a WSTL-key. So I'm going to just qualify this really quickly as a student, and that should clear that up. Okay, so now we're good. We have this binary search tree that goes from student to string. Okay, let's write a function next that's going to add students. All right. So I'll move this down. I'm going to add in Bruce Wayne, Peter Parker, Diana Prince, Clark Kent, and Bruce Banner. They all have these WSTL-keys, as you can see. And the behavior of this function that I want is it's going to add in a new student. And in this case, if I insert a new student in, I'm not expecting any collisions on this these keys. So let's raise an error if that ever happens. Okay, so that'll be sort of just a way for us to use what the binary search tree returns to us for insert. So rather critically, let's build. Let me make a let expression, and then I'm going to make. Excuse me. I'm going to just make a new val binding that is going to be our stu. And let's just really quickly make first name field is going to equal the first name. Stunning. Last name is going to equal last name. That was nice that it actually fixed that for me. WSTL-key is going to be WSTL-key. Let's start off the barebox balance at 0.0, and let's make your courses be empty list. And then let's just insert it into the tree. So there's going to be something here. We'll just fill that in as nothing right now. And we're going to call binary search tree. Oh, sorry. Binary search tree dot insert. And I'm going to insert into this binary search tree that I was passed in stu. And what that's going to return to me, let's fill this in now. That's going to return a tuple, one of which is the binary search tree prime. So that's the new tree that should have stu in it. You know, that's an updated tree. And then also this other thing, which is going to be a previous student, like what's the previous stu, and it's an optional, right? So if somebody matched this guy's key, it'll return you back what it just replaced, okay? And that would mean that there's going to be two people with the same WSTL-key. We obviously want to prevent that from happening. So let's get a case expression going now on this option. If that's none, everything's cool, right? So let's return the binary search tree prime, right? That means, by the way, there was nothing in there. Everything's cool. There isn't now two people with the same WSTL-key. And otherwise, it's like sum of like what actual previous stu was. Let's raise an error. So raise, we'll just do fail WSTL-key already allocated to. And again, I'm going to just do some, again, I didn't pull it out into the full record, so I'm actually going to use the syntax that I actually don't really like that much, but I love pattern matching, and now my examples are all using this other thing, which is most bad. Makes me feel bad, but you'll all forgive me. And first name, I just can't do hash first name. I need to do hash first name of prev stu. And let's then append onto it the last name. Okay. Last name. So if that's going to be our add student. If I run this code right now, let's see, I actually have a syntax error here, so it's or else. So I have none for that. This is raise fail of that. Let's see the actual error line, 18, which is not, oh, I didn't take that out. Okay, so now we're in good shape. We're doing this binary search tree. It's working for everybody. We'll print out its contents in a second. If I try to, so Bruce Banner somehow took Gamma Ray as his ID, which is fine. And then Ray Gamma shows up, and poor Ray is expecting to steal the Hulk's ID, which is not going to go so well. That throws a right paren error on me. Oh, because I need to comment out the rest of the thing because I have a close comment at the bottom. And you can see it's, let me put a space in here. It's saying, oh, this, we tried to add it in, but because insert is returning both the new tree and what the previous student is, I'm able to give this nice thing that says, this inserted, it worked, right? But I'm not going to return you this different, I'm not going to return you an invalid tree, right? I'm going to raise an exception and not ever return this information to you. Okay, and so let's just say that poor Ray Gamma comes up with a new name. He's not going to get it from the Hulk, that's for sure. Okay, so let's print out this tree in a little bit better form. You can print out, you can convert binary search trees to string, but you have to provide this function which turns your value type, your alpha, into a string. And we could do that, but we would have to do that for this entire structure right here. So let's just convert it to a list, and it'll print out a little bit better than what's printing out down here. So, and plus it's nice to be able to convert it to a list because we can determine that it's in the correct order. So let me just do this first. We're gonna use fold in this case. So binary search tree.fold, and you could do LNR or RNL. RNL does it right first, which works great for cons. So let's just do that because we're converting it to a list. I'm gonna write it as an anonymous function first. You obviously don't have to do that. And we're gonna do, well, excuse me, it makes sense to do it this way as an anonymous function, but we can do a little bit more clean in a second and not unnecessarily wrap this function, which is kind of crazy. I'm going to just do this anonymous function and const do onto the accumulated list, pass in the list, and I have to pass in the tree that I actually want to fold as the final thing. So let's run this. And now, oh, I got an or else here. So I'm going to fold. That's my function. Undoubtedly, I'm going to have to wrap these things. You always have to wrap these things in parentheses. It was rather bold of me to assume that I didn't have to. And now, let's see, we can see that we have, let me grow this up a little bit. You can see that we have each of the record values, right? And they're in sorted order. There's by their Wustel key. There's Amazon Diana, Gamma Ray, I Am Superman, Wayne B, and Web Slinger, all in there. Everything's fantastic. And so this is working. What I was alluding to before is like, this doesn't seem like the most terse thing ever, but if you can see, this is a function that goes from stu to, a list, a student to a list, and then like just calls cons on those two things. If I try to pass in cons, that's a little too aggressive. That's not going to quite work because it's like an operator is not a function. They do have it so that there is a function for use. You just have to qualify it right here. And then I could just pass list dot, the list module, colon operator, and that works. Now, whether or not you think this is a little more confusing than the function, the anonymous function, is up to you, but I'll just leave that in there as a, one of the students actually brought this up for, you could do this for greater than too. It wouldn't work with obviously a list and like what we're using, but you can just pass in these things, even cons, as a function, which is kind of great. Okay, so let's move on. So that's fold, converting it to a list. So that's great. Let's work on find now. So I want you to imagine the following. We're going to call binary search tree on prints D. Let's expect like Diana prints. That's what we thought her ID was. That isn't it. It's Amazon Diana. But let's do this. We should find that we expected none and we got none. So like calling find on this is going to return an optional thing back, whether or not I actually found it. And in this case, I'm going to pass in the right key, and I expect Wonder Woman, and I'm going to get Wonder Woman, which is outstanding. There she is, all of her information. I get the full value back in this optional. Same thing sort of happens with remove. Okay, so I'm going to call remove on my binary search tree with, say, the wrong key, like Clark Kent, Clark K. Here, I'm going to expect none back. When I actually remove it with I am Superman, his actual WUSTL key, we will get back Superman. This BST thing that is updated here now will no longer have Superman in the list because we removed him. So let's see here how that goes. Now, there's students has this information in it now that I've printed out. I could say this without Superman and not shadow it. And so just to sort of emphasize that, like, students all know super, that I didn't mutate this binary search tree. This one that is coming out is the after remove is gonna this one is gonna have Clark Kent in it. I am Superman. This one doesn't because we took them out. Okay, just to sort of clarify that, you know, it's not mutating this guy; it's returning a whole new one. All right, with that, let's move on to our final function we're going to use, and that's going to be to update bearbucks. And what I want you to imagine here, it's not unreasonable to think if you were actually building university database that, you know, there might be some refs in here. You'd let people like add and remove courses. Bearbucks might be a ref to a real and you mutate it. As it stands now, student is immutable. So this function I'm going to write update bearbucks is going to just insert a new, it's going to build a whole new record and insert it in and replace it, okay? And unlike in add student, where we're like, oh, that's an exception, right? Like I'm not expecting to add a student with 2 WUSTL keys. In this case, we're fully expecting that it'll be in there in the first place. And then once it's in there, we're going to replace it and we're going to expect that to come back and still be full. In this case, I'm going to just call binary search tree and I'm going to find my WUSTL key in this binary search tree. In case of, if that comes back as none, excuse me, I'm going to raise, I've made a couple of exceptions here, one that the person's not found and one insufficient funds, which we'll check for that in a second. So if it's none, let's just raise not found. And honestly, this should be of string. So let's do that right now. And we'll say not found of the WUSTL key. Otherwise, it's going to be some of, and now here comes my big record. So it's going to be first name, and I'm going to expand the environment to include first name there. Very exciting. And last name is going to be last name. And I have to do this, right? Because I'm going to build a new record. So I need all the information that came with this key. Okay. I could, for WUSTL key, excuse me, WUSTL key, I could expand that into like prev WUSTL key, right? And check it against WUSTL key. That seems reasonable. If you're building this database, you might check to make sure everything's sane. I'm just going to say, like, let's assume that's okay. We're not going to spend time just checking that. But you could imagine like throwing an exception if these things didn't match. That would be an error. You'd be like, wait a minute, this binary tree is broken. Bearbucks we're definitely going to want. I'm going to call this prev bearbucks because we're going to update it in a second. And then the other one is going to be just courses, and I'm going to need that also. So I'm just going to grab that into courses. So that is going to be that branch. I need to write what we're going to do when we handle that. Like I said, we're not going to check to make sure those were the same, but we are going to check to see if the bearbucks that you're that you can actually do this transfer, right? Like if this is negative and it drops below 0, we're going to want to reject that exception. So as I'm sure the university would do. So let's make something called next bearbucks. And that's going to equal pre-bearbucks plus this delta that I'm trying to apply. And then that's going to be in, and I'm going to say if next bearbucks is less than 0, then raise some insufficient funds exception. And you can imagine me just sort of saying, oh, like, by the way, you've gone negative. And so in this case, I'll just say, well, let's actually do a good job while we're here. Let's do balance and is real dot toString pre-bare bucks, and let's add on to it attempted arrow delta, which failed that delta. Okay, so that's just going to be that quick check. And now let's build another let expression with some other things in it here. And okay, so now this is going to be the part where we actually do something. Let's build our next student. So val next student, and this is going to be something that looks a lot like this. We're going to take the first name that we draw out, the last name that we drew out. We're going to put the WUSTL key as the WUSTL key that we were passed in. It should be the same as this guy. I just didn't check it. Instead of pre-bare bucks, we're going to make it the next bare bucks, and we're going to keep the same courses. Okay. Now, as a bonus, let's just do this. Let's call. Let me just say we're going to fill this in a second, but we're going to do binary search tree insert on this next student. Okay. And maybe I should call this updated student. And either way, it's nice. It's actually updated. Sounds like I'm mutating it. So like we'll call it next student. Insert into my binary search tree this next student. Okay. What that's going to return is just like the last time, it returns the new tree and the previous student, right? Which should be this guy, right? So again, we could check that. I'm going to ignore it for right now because this video is already going on pretty long. But that's in the other case, we were actually checking this and worried about it. Now we're like, okay, it's going to be the same here. So let's just move on. And I'm going to have update bare bucks return the updated binary search tree, right? Because like that's the whole point is I'm building a new one based on this new bare bucks. And I'm just going to pass back pre-bare bucks and next bare bucks just to provide as much useful information as I can. And in this case, I want you to imagine, let's see how this works. Let me run this, see if this goes. And caught exception compile, I'm missing a right paren. Always a possibility when you write from something this long. So it's saying on 59, which makes some sense, this end tragically. I am missing, oh, syntax error inserting let. I forgot to end this let. Gonna be it? Okay, so now I fixed that one, I guess. And 72 now, oh, I had a dangling comment. Okay, so now we're into our real things. So now somehow I have operator and operand don't agree. So this is always dangerous. And this is going to be that this is not an int. Now it's string to real. I have yet another error. So always like when you do something here. Insufficient funds balance. I'm going to add onto it real to string like pre-bare bucks, right? And then I const onto that and delta, and that is not a string. I need to real to string that delta. So you get used to all the stuff that other languages do for you. And ML is not really into like taking reals and turning them into strings automatically for you. You always have to sort of explicitly do that. So here we go. We got this whole thing. I'm going to just, this is sort of working now. You can sort of see that I've converted to list, and now you can see that Batman has decided his zero balance is not good. Poor Peter Parker, not a lot of money. He's only got 2 cents. And so now if one last thing, or Peter Parker goes and tries to buy a burrito at the Duck. Remember in the world when we used to be able to do that, and now we throw this exception. And so of course, maybe we'll just imagine that Batman hooks him up and buys him a burrito. Okay, hopefully that clears up a few things about the binary search tree. And why we have this alpha kappa, you know, why we have two types for this thing. The alpha is the value at each node, and the kappa is going to be the key that we search on.